Have you ever been abroad in a seismic country and looked at all those really old buildings and wondered, how is this still standing? It seems crazy, right? You can look at buildings that are 100, 200, and even 500 years old, and some of them can look almost intact in terms of structure strength. But how did they manage to achieve this centuries ago? First, let's review some basics. When massive fragments of rock in the Earth's crust slide against each other, earthquakes occur. These shifts release huge amounts of energy that travel through it as seismic waves, causing the ground to shake. Earthquake forces act in all directions, up, down, and sideways, leading to tension, compression, shear, and bending. Historically, there were two main approaches. Load-bearing elements were designed to absorb and transfer seismic forces back to the ground. These could include beams, lintels, vaults, columns, and walls. The effectiveness of these elements depended on weight distribution and following a clear load path, which is the route by which a building's weight and forces are transmitted from their point of application to the foundation and finally to the ground. Strong connections between building elements were crucial as they allowed force and displacement to be transferred between horizontal and vertical elements, allowing all elements to act together as a unit. If beams and columns were well connected, they could resist the rotation and lateral movement caused by earthquakes, transferring forces down to the foundation. This type of connection is known as rigid frame action, where the entire frame of the building works together resisting seismic forces. For example, in Japan, in the Horiji region, there is a temple featuring a shimbashira, a large central column that acts as a shock absorber, stabilizing the structure during an earthquake. Masonry involves constructing buildings using stone, brick, or similar materials, and often interlocking them. Masonry walls needed to be much thicker than modern walls as they help distribute the forces during seismic activity by relying on the weight and arrangement of the materials themselves. Some notable masonry techniques included ashlar masonry, rusticated masonry, and cobblestone construction. An element's strength is its capacity to withstand force without failing or breaking. The ability of an element to resist displacement when subjected to an external force is known as stiffness. Let's take this glass for example. See how it's difficult to bend it but very easy to break it? Therefore the strength is low but the stiffness is high. And this spring from this pen, for example, it's easy to compress it but very difficult to break it. Therefore the strength is high but the stiffness is low. During earthquakes, the stiffer element tends to bear the total force of two elements with varying stiffness because it requires more force to deflect. Therefore, masonry walls were built as the interlocking nature of the stones and the thickness of the masonry added to its rigidity. For example, the ancient Indians used dry stone masonry, where stones were precisely cut to fit together without mortar, allowing the structure to absorb and dissipate seismic energy effectively. Another example was the donggong system in traditional Chinese architecture, which consisted of interlocking wooden brackets that allowed buildings to be both flexible and strong. Today, though technology has evolved, the principles kind of remain the same. Modern buildings still focus on flexibility, energy dissipation, and strong connections, just as ancient builders did.